2022, I have not seen it in the syllabus. It's called combination of springs. So series parallel springs, okay, you can combine springs in a different manner. Oita is like very common MCQ question. And if you don't know how to use the formula, those MCQs will take you 10-15 minutes, right? So, you don't have that time. So it's quite just for the safety of it. Right, so আজকে নতুন একটা জিনিস করবো, সেটা হচ্ছে চ্যাপ্টার 6.1 স্ট্রেস এন্ড স্ট্রেইন কি হবে এখানে আমি বুঝাচ্ছি তোমাদেরকে, জাস্ট একটু দেখে নিই। Right, so can you go to page 4? এটা page 4 এ add হবে। It's a very interesting একটা topic এই wordটা। All right, so screen এ কিছু লেখো না, বুঝার চেষ্টা করো। It's a very small topic, like really small topic, but absolutely everything is new here. Okay, so that's why we need to be a little careful. So এটা হচ্ছে material analysis. Okay, so what is material analysis? Let me explain. So essentially, we started off on a wrong foot with materials. I'll tell you why. We learned what initially? Springs. Remember, all levels of springs, and springs bhaloi bujar kotha by now. We have done it twice. So springs hocche stretch korle force will extend kore, right? And it undergoes elastic behavior, and it's also proportional, which means that it shows what property or what behavior is obeyed by it. Hooke's law, right? So Hooke's law states that it's proportional and also what? Elastic. So Hooke's law hocche ki? Hooke's law states that a material is both proportional মানে কি, will give you a straight line, and also at the same time it is also what in nature? Elastic, right? So we learned about springs, but one very important question was missing, যেটা ও লেভেল থেকে করো না এখনো কেউ করো না, is what is a spring made up of? So spring কি হচ্ছে periodic table এ কোন গ্রুপে পাবা springs? No, it's not an element, right? What is it? It's a shape. Spring is a shape. It has nothing to do with what the material is, right? So it could be made up of, this one is, for example, made up of aluminum, right? It could be made up of iron. It could be made up of copper. It could be made up of many different things, right? But we don't really deal with that. What do we deal with? The shape, right? এখন এই same copper বা aluminum I can make like a very big spring. Our behavior completely different, despite this and that being made up of the same material. You get my point? So does that mean that when we deal with springs, are we dealing with the material or the shape? Shape, right? And that is actually useless when it comes to actual practical application out there. Springs are not really used that often. In many places, use kora hoy na to, right? But what we use everywhere, literally, materials, right? I'm using materials for my furniture, the building, whatever I build is built with materials. Materials মানে কি? Different element, different combination of elements, alloys, right? Oiter property is more important for us than this shape out here, right? So why did we learn this? I mean, the board and the examiners, they know better. They should have started with the material, right? Problem hocche, materials don't obey Hooke's law, and Hooke's law shikata more important for us. That's why what did we start off with this, right? In fact, spring day invent course, Robert Hooke, right? The Hooke's law is named after him. He basically made this shape so that this shape obeys what and what behavior? Elastic and proportional, which is very rare in real life. You will barely find anything that does both. I think I showed some examples here, remember. We saw a rubber band, which was what? Elastic, but what wasn't it? Proportional, right? I showed you clay, which was proportional. What wasn't it? Elastic, right? So most materials are like that. In fact, I would say 99% materials do that, right? But this shape does both. That's where they start, right? এখন আমি তোমাকে একটা জিনিস দেখো, just try to understand. I'll tell you like a problem, see what the issue is, okay? So here's the issue. The thing is, I want to construct a bridge, and bridge বানানোর জন্য they use iron, like different types of iron, like grades of iron, right? So iron use করা হয়, and I saw a bridge that I want to replicate. মানে একটা bridge কে দেখছি ওটাকে replicate করতে চাই, and I asked the person who built the bridge at what kind of iron did he use, like what's the property here. So according to him, iron rod এরকম দেখতে, okay, and when force was applied on this iron rod F, the iron rod underwent extension as it should. So that's the extension out there. Right. So what is this made up of? Iron. Are you with me so far? So it's an iron rod. যেখানে আমি force F করলে, what does the rod do? Extend X, right? এখন I want to build a bridge, and I want to follow this person's guide. Somebody build a bridge using iron, right? So she আমাকে বলছে that if you have this rod here, right? এই রডটার মধ্যে যদি force F দাও, তাহলে extension X is fine. So what I did was I went to the supplier. I got an iron rod, and iron rod দেখতে হচ্ছে এরকম. It's thicker across section. But everything else of the iron rod is exactly identical to what the person told me. So I'm using the exact same iron rod, same iron material, everything same, literally, except for one thing. But it keep different cross section. Okay. Now you tell me, and this is common. You don't need to go very deep in the chapter to understand this. Can you tell me if I apply force F on this particular piece of iron, right? Do you believe it will extend the same amount, more or less? It's intuitive. It's less of because it's a thicker material. Your force is not being exerted the same intensity. Like a thinner material, stretch for easier. I'm not asking you to look for science. I'm just asking for practical experience. What's easier to stretch? A thick object or a thin object? Right? Thin objects take much easier to drive, right? Here's the problem. আমাকে বলা হয়েছিল যে force F দিলে, what was the extension? X, right? So I followed the person's instruction. My iron rod is exactly the same length and everything. Kintu, when I apply my force F here, what is the extension here? Not the 1x anticipated, right? And turns out it doesn't make my bridge work the same way. দুজনের behavior different না? Can you tell me what was the property that I completely disregarded, which was a big factor? Cross-section area, right? Acha, fine. So the cross-section area somehow turns out to be important. We completely ignored it. At the spring, যখন আমরা compare করি, have you ever used cross-section for your investigation? No, right? Did you ever mention Hooke's law that F equals to kx এর মধ্যে what the cross-section is? No, right? Because it didn't really matter. But now we see it matters somehow, right? Okay, fine. So I agree with the person. The cross-section actually now you guys told me. So এখন I do the same. But this time I take the same material, just same iron and everything. But I use a smaller length, because I thought cross-section area is the main factor, right? And I take a smaller length of this wire, and I apply the same force F here. Okay, the same force F apply korlam. Again, based on your common sense, actually, cross-sectional area is what as before, same. What is not same as before? Length, right? Do you think this will stretch as much as the original material? এই যে এখানে যে x যেটা ছিল, এটা কি সেম ভাবে stretch করবে? No, why not? মানে what's easier to stretch, a small object or a big object, a short object or a long object? Longer object বেশি material না, so isn't it easier to stretch? If I give you like a very small piece of Play-Doh versus I give you like a big bundle of it, right? Wouldn't the big bundle be very easy to stretch? And if I take you like give you a very small amount of it, wouldn't it be very difficult? Because it's lacking material to stretch, right? So now what turns out to be also a factor? Length, right? Length কোনোদিন আমরা কিন্তু use করতাম না. In fact, we used to be like never use length for springs. When I say what was the value that we always wanted to use for springs? Extension, right? Turns out length is also a factor. Now eventually যেটা বের হয়েছে, this is the summary of everything. When you want to compare material, F equals to kx fails. If I just use F equals to kx, তিনটা material কিন্তু আমি F equals to kx apply করছি. Did I get this same x for each material? No, right? মানে আমার কিন্তু এটা একটা extension, এটা একটা extension, এটা একটা extension. What's the problem here? Problem হচ্ছে I use what material for each of them? Iron use করছি না সব জায়গায়. Why is my iron behaving differently every time? Isn't that a problem? Like it's difficult to compare. So imagine you use steel and I use steel for some kind of structure. এখন তুমি আমাকে খালি বললা যে আমি 10 নিউটন প্রোভাইড করছি স্টিলের উপরে, আর কিছু বললা না how long or how short. Do you think the steel rod I have will behave exactly same as your one? No, right? Because what information is missing? Cross section, length, right? কিন্তু স্প্রিং এ কিন্তু তা না. স্প্রিং এ তুমি যদি আমাকে বলো যে হচ্ছে force 10 দিচ্ছ and the extension is like that, spring constant একটা ভ্যালু বলে দিলা, and I follow that, my spring will do the same thing. Spring constant literally means how much force makes what extend, right? So what's the issue here. Issueটা হচ্ছে a f equals to kx টা fails us in comparing what materials. So আমাদের দুইটা কোয়ান্টিটিকে ইনকর্পোরেট করতে হবে। একটা হচ্ছে কি area and the other one is what length, right? And that's where what we do is we upgrade f equals to kx. And now listen very carefully. Okay, this is where the chapter starts. How do we upgrade this formula so that it helps with materials? So যেটা আমরা করব, আমরা হচ্ছে ফোর্সটাকে আর ফোর্স রাখবো না, we will upgrade this to a quantity referred as stress. Stress হচ্ছে how much force you're exerting over the cross-sectional area. So what have I incorporated into my analysis right now? Cross-sectional area. So just force now, what I'm rather trying to see right now is what? The force acting over an area, right? এটাকে stress বলা হয়, এটা unit কি হওয়া উচিত based on your knowledge? Meter square, right? Isn't that the same as Pascal? So stress is same as pressure. Acha? So it's basically a measure of how much your force is concentrated. Okay? So আমি যদি এখানে ফোর্স অ্যাপ্লাই করি, এই যে বড় মেটেরিয়ালে ফোর্স অ্যাপ্লাই করলাম উপরে আর এই ছোট মেটেরিয়ালে ফোর্স অ্যাপ্লাই করলাম উপরে, where do you think is the pressure more? Yeah, so wouldn't the smaller one experience more force per unit area? So it's easier to stretch, right? You get my point? Okay, next হচ্ছে এই extensionটা is also flawed. You know, the extension just tells me how much it extends, but what is another factor that is a big factor? The length, original length, right? And from there we come across a quantity called strain. Strain হচ্ছে the extension that your material undergoes divided by the length of the wire. And এটা একটা percentage, এটা কোনো unit নাই, এটা percentage হিসেবে বলা হয়. And why is it very helpful? Listen to this, okay? I have a material that stretches 5 centimeter. I have another material that stretches 10 centimeter. 5 centimeter, 10 centimeter for the same force, okay? Can you tell me which material is longer? একটা 5 centimeter stretch করে আর একটা 10 centimeter stretch করে for the same force, right? Which one is longer? Right, the correct answer is inconclusive. I'll tell you why. ওই 10 centimeter টা হচ্ছে হইতে পারে thicker, but ওটা cross section হতে পারে কি much smaller, right? So if you don't know the original length, you can't really compare properly. But also, what else needs to be known? Cross sectional area, right? Percentage টা কেমনে help করে? If I told you the strain of a material is 15%, মানে হচ্ছে 100 centimeter যদি তোমার length হয়, how much does it extend? 15 centimeter for a particular force, right? 200 centimeter hole, how much will it extend? 30 centimeters. So do you see how it compares, right? এখন আমার যদি হচ্ছে strain হয় 90%, এই কোয়েশ্চনটা তোমাদের জিজ্ঞেস করেছে, একটু দেখো পারো নাকি? Can you tell me which material here is very ductile? Have you heard of the word ductile? Something that can be easily stretched into what? Wires, right? So can you tell me which one here is very ductile, like a 90% strain or 15% strain? Yeah, 90%. What does 90% mean? That for every centimeter or for every 100 centimeters, how much does it stretch? 90 centimeter. Our material, 100 centimeter, how much does it stretch? 15, right? Which one is very easy to stretch? 90, right? So strain basically tells you like a return on how much you get for the length available. Okay, so I'm just such a numbers that to give you some idea what's happening here. So we have an improved version of force, which is what? Stress. An improved version of extension, which is strain. That means there must be an improved version of what as well? Spring constant. And a spring constant to spring, right? So for material, there is actually an improved version. It is called the Young modulus. The Young modulus is the improved version of spring constant. So now here is the thing. If I want to compare two springs, right, what do I normally compare? Spring constant, right? If I want to compare material, what do I compare? Young modulus. And why is Young modulus far superior than a spring constant? Young modulus is unique for every material, not for shape, not for length, not for size. It's unique for what? Every material. So if you take a small piece of iron and if you take a rod of iron as the size of this room, right, and you find a Young modulus for both of them, what value would you get? Same value. Isn't that much more reliable when you want to compare? Because now it incorporates every property out there. So why is Young modulus the ultimate way of comparing materials? It takes into account every possibility of a material and gives you a value. And that value is unique for that material. It is exactly like density. Remember density? Density was what? The property of a material. আমি যদি mass change করি, volume change করি, density সবসময় কি থাকে? Same, right? Same goes here as well. Young modulus, Young modulus, Young modulus. Every Young modulus of the material of iron has what value? Same value. And once you want to compare materials, you just compare their what? Young modulus. It's easier to do that. Okay. So yeah, that's the start of the chapter. In fact, I could say it's also the end of the chapter. Quantity নিয়ে কাজ করতে হবে, ওটা অ্যাপ্লিকেশন একটু দেখাতে হবে তোমাদের। সো ইয়াং মডুলাস ইজ সিম্বল আছে তোমাদের, সিম্বলটা মনে না রাখতে পারে, জাস্ট রাইট দ্য হোল ওয়ার্ড। এফ না 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 আমি দেখাচ্ছি। ইয়াং মডুলাস ইকুয়ালস টু স্ট্রেস বাই স্ট্রেন। সো এটা হচ্ছে স্ট্রেসের সিম্বল হচ্ছে এপসিলন আর স্ট্রেনের সিম্বল হচ্ছে সিগমা, and এটার ইউনিটটা হচ্ছে প্যাসকেল, এটার ইউনিটটা হচ্ছে প্যাসকেল, and strainer unit কি? Nothing. Okay, it doesn't have a unit, so there's no canceling out going on here. There you go. So formula লিখে নাও, then I'll give you definitions of each of them. Stress strain graph একটা আছে, গ্রাফ করতে হবে। সিগমা হচ্ছে ইউনিট না, সিগমা হচ্ছে এখানে সিম্বল, ইউনিট হচ্ছে কিছু নাই, but yeah, sigma is very often used. Square bracket টা লাগবে না, স্কয়ার ব্র্যাকেট এমনি দিছি, স্কয়ার ব্র্যাকেট নাই। No, if your material is hollow, the stress will be different because it's hollow, right? Acha, you meant like solid but ভিতরে খালি? না, তোমাকে ওই ends গুলোকে বাদ দিয়ে ক্যালকুলেশন করতে হবে, because basically it's like a cylinder and you put a lid to it, right? And you're applying force. ওই lidটা তো is not consistently everywhere. So what's consistently everywhere? Just the ring. তো ওই রিংটা নিয়ে কাজ করতে হবে। So তুমি যদি একটা হলো টিউব নিয়ে হচ্ছে ব্রিজ বানাতে যাও, would it be stronger or weaker? Weaker, right? So because তোমার হচ্ছে assumption হচ্ছে যে shape এরকম, but actually the material নাই ভিতরে। So normally হচ্ছে middle cross section নিয়ে কাজ করতে হবে, or the average, right? Oval cylinder, মানে it's a cylinder but the cross section is oval, or that's not an oval cylinder, the one that you're trying to show me, that's an egg. It's an egg, right? That's what it, okay, a metal egg, that's what you're looking for, right? Yeah, you have to take the widest area. No, হ্যাঁ, তার জন্য ক্রস সেকশন নিয়ে করতে হবে, থিকনেসটা নিয়ে কাজ করতে হবে। Simple করে টু উল্টা হবে, okay? Sigma is down here. Or epsilon not just strain. There are around 9 definitions on this topic, ওইটা হচ্ছে আমি একসাথে দিয়ে দিব. Some of them we have already done, like limit of proportionality, elastic limit, Hooke's law. নতুন add হচ্ছে stress, strain, Young modulus. আরো তিনটা add হবে. Okay, so we have toughness, strength, and UTS. Forgot the number, something like 50 or 60. It was I don't know. No, we stopped counting. It's like everything is a formula. Yeah, stress is force, but over a certain area. Why? Because when you just apply force and you ignore the area, we find that the material behavior is different. So that's why what did we want to take into account as well? Area. And strain is extension, but it's extension over a certain length. Why? Because we find that if you take the same cross section, same force, right, but different length, the extension is different. So doesn't that mean the length also matters? So that's why we incorporated the length into my math now. So that gives us strain. And using that stress and strain, we get a new improved spring constant called Young modulus. Yeah, partly yes. Strain জি বের করতে চাও? Extension মানে ম্যাথ করে নাকি হচ্ছে ফর্মুলাতে ওই স্ট্রেন ইউজ করতে হবে. হ্যাঁ. So length and cross-sectional area is important when analyzing materials behavior. Correct. It's not important for a shape যেমন spring. Okay. Young modulus is a property, yes, correct. Well, how do people come up with what? Easy. Yeah. কিছু ছিল না আমাদের? This is a 5,000-year-old material property that you're looking at. 5,000-year-old people, there are tissue parts of Nora, যদি ভাবছে it's possible. তোমার একটু ডিসকাস লাগতেছে কেন? যারা pyramid build করছে, they knew this. That's why they didn't give it a number, but they knew how to compare material. Otherwise, they didn't build your pyramids with clay, right? Why didn't they? Because they were more practical. Are you guys done? Any questions? I'll just clarify. Key done. Stress strain Young modulus. Do you understand these 3 quantities so far? Right? What they mean? I'll show you applications of them, but these are quantities used to compare material behavior. Okay? Right. So, যেটা করব এখন, can you go to page 5? Not further. It's only applicable for the material of the spring. So, যদি স্প্রিং অ্যাপ্লাই করতে চাই, আমাকে যে মেটেরিয়ালটা সেটাকে খুলে প্রথমে স্ট্রেচ করে একটা ওয়্যার বানাতে হবে, তারপর আমি মেটেরিয়াল অ্যাপ্লাই করতে পারবো. Okay, screen কিছু লেখো না. Let me explain what's going on here. So you have a graph here for stress, versus strain. And when I want to compare materials, just raw number doesn't really help a lot. So if I told you young modulus of something is 5 and something else is 10, right? It doesn't really help much. You need to see the graph, like overall variation. So how does the graph look like for 3 materials? We have 3 materials in our syllabus that we need to look into. General materials, metals, glass, and elastomer. Elastomer মানে হচ্ছে hydrocarbon based materials like plastic, rubber band, those kind of materials. Okay, their graphs are very unique, and their graphs are always the same because young modulus values are always what for the material, same, right? So the most classic graph from this topic is the one for metals. It looks something like this. Okay, so that's the graph, and then we need to know why is it like that. So প্রত্যেকটা part হচ্ছে দেখতে হবে আমাদের. So this is a graph for a metal. If you understand the graph for a metal, right, you'll understand all the other materials very well because it has every property in it. Okay, so glass property, elastomer property, সব কিছু metal পাওয়া. Okay, so let me show you how. So if you look at this graph here, and I want you to tell me what's going on here. This early stage here is the one that I'm highlighting right now. Is the line straight line or is it curved? Straight line, right? So it means stress and strain are directly proportional to each other. Do you agree? It means that there is a point on this line till which the graph is a straight line. What do we call that point? Yes, limit of proportionality. What is limit of proportionality? So limit of proportionality is the point in which the force and extension is directly proportional, and force and extension they derive kori stress and strain. So stress and strain do directly proportional. What does that mean? It's limit of proportionality till that point, right? So this point that you see here is your limit of proportion. But here's the interesting thing. Where is my elastic limit? So where is the point till which this material, if stretched and force is removed, won't come back? Where is it? The end point, right? So I made a both sum, but you guys forgot. You can't find it from a graph. I mentioned this. If you look at a graph, there's no way to say where the elastic limit is. Cannot, because it could be anywhere. I can only know where elastic limit is if I know how did the material go back. So if it doesn't go back to the origin, I know that the elastic limit is somewhere else, right? So right now it's not possible, but there is a hint. A hint this is a unique thing about this graph. If you look, there's a flat part here, the one I'm highlighting right now. A flat part is called the yield region. Okay, yield return, yield region, right? It is usually, and by the way, this is not always true, but usually the start of the yield point marks the end of the elastic limit. So একটা elastic limit যখন তুমি cross করবা, material কিছুক্ষণ flat থাকে, young modulus graph, and then it peaks again. Why does it remain flat? I'll explain. They don't normally ask for it. I'll explain still. That is usually where the elastic limit would be. So my question for you is, can you tell me a graph till which point does the material obey Hooke's law? Till the A or B? Yeah. Why? Correct. So till the point A, is the material proportional? Yes. Is the material elastic? Yes. And isn't that the criteria for Hooke's law? So the material obeys Hooke's law till this point. So this point would be my what point of the graph? Hooke's limit. Okay. I just want to clarify one more time if you missed the previous classes. Hooke's limit doesn't need to be at the same place as elastic limit and limit of proportionality. It is only at the same place for what? Springs. Okay, that's the unique thing about springs, right? So এটা এভাবে যাচ্ছে, and then the final point that you see here, it is when the material breaks. So that's called the breaking point. And a valueta, this highest value for stress, this value is called the UTS. এই পয়েন্টটা এটাকে বলা হয় UTS. UTS মানে কি? Ultimate tensile stress. What does it mean? The maximum stress your material can withstand. So কি কাজে দেয় এটা? The UTS, it's to compare the strength of material. So if you want to know what's a strong material, right? কোথায় problem? I'll show you with practical scenario. If you look at this, these both are made up of wood, right? Which one is stronger? Which one do you think is difficult to break? Eta? But what are they both made up of? Wood, right? Why is their behavior different? Yeah, because of length, cross section, and everything, right? So I'm যদি এদেরকে as material না নিয়ে as shape compare করতাম, wouldn't I get two values for wood? You get my point? মানে দুইটাই তো wood কিন্তু, but দুইটার value different আসছে না? extension, force, stress, strain, stress, strain, sorry, the force needed to break and everything. So what's the issue here? Why can't I compare the two materials? Because I'm not comparing like for like. You get my point? At a different shape, at a different shape. But if I found a UTS for this, and if I found a UTS for that, you'd find that they give the same stress. Stress into force. Stress is what? Force by area, right? So আমি এটাকে UTS যদি বের করতে হয় কি করতে হয় বলি, এটা তোমাদের সিলেবাসে আছে, you have to hang it from a ceiling. So if you go to mechanical labs in universities, you'll find that 3-4 tala height হয়, you know, they hang stuff from the ceiling, and then what they do is they keep adding masses here, and at one point what will the rod do? Snap. That snap is the break. Okay, আমি যদি এটাকে এভাবে break করি, like that, right? If I snap it that way, that's not the right way of breaking material. That's not the right way of testing material. How do I need to break it? By applying force at the cross section. It is not applying force at the cross section. You get my point? So it again, UTS break what do I do? I need to hang it, right? And we can take mass suspense at the point keyboard notice it snaps into two pieces. That's when this graph goes up. A graph really plot you have to do it this way. That's the right way of doing it. Are you clear what I'm trying to say? Because there are techniques out there where you can break things easily into, like, turn, twist, and snap, right? Take like hacks. These are not the right ways in material. I'll show you again. But what I want to say is that if I want to compare material, right? You don't compare the force needed to break that. You compare the what needed to break that. Stress. Clearly, the compound force. I would have force, but we don't think big stress like it. Same. If they're wood. Okay. And that's easy to compare. Same with the same material. No. So I would compare it, right? So now let's say I take here and I take plastic. The UTS is different. The UTS on the low, the UTS on the high. Which one is stronger? If you build a bridge entirely identical using this, which will be stronger. Yeah. So that's why we compare. The different material compare. Right. So this is the UTS. Our thing is that I haven't really seen this in your syllabus. A chapter to be vague because they made so many changes over the years. I'm not really sure where it stands right now. So shall we call it a area under the graph. So this area under the graph actually means something very important. Okay. So the area under the graph here, key mean for a date program, right? So do you guys remember how to find what area provided us using math? Motion chapter শিখেছিলাম. Like let's say you're given a random graph and they ask you what the area provides, right? What would you do to find what the area provides? Very good. We compare their axis, right? Come gradient to the very put don't I divide the y-axis quantity by the x-axis quantity and give me what the gradient would be, right? A graphic gradient কি দিবে? A graphic gradient. Young modulus, very good. Because such a gradient they start kori ami eta jodi gradient ta ber kori, wouldn't that be change in y by change in x? What is my y-axis? Stress, and x-axis is strain. So the gradient of this graph gives us what? Young modulus. But when you bolam na just young modulus jodi ami compare kori, isn't that a half told story? There's so much more going on, right? So ogla jonno ami showing the rest of them. Okay, now area kemne compare korbo? What do we do with area? So area jonno what you need to do is you need to multiply the axis, stress into strain. Can anyone tell me what is the unit for stress or formula for stress? Force by area. And what is the formula for strain? Extension by length, right? So eventually what we end up here with is force into extension divided by area of the material into the length of the material. Can anyone tell me what is the area of the material, cross-section area of the material multiplied by the length of the material? Volume of the material, right? So it a volume share. What is force multiplied by the amount of extension it undergoes? Force multiplied force by extension or force into extension. Yes, it's the work done, right? And a property is extremely useful for comparing material because it gives you something that has a unit of joule per meter cube. এটাকে বলা হয় energy density. What is energy density? Energy density হচ্ছে a material. Yeah, it tells you how much energy is stored per unit volume. Okay. My class can do till 5:15 down. Yeah, I posted in Google Classroom. So aru 15 minutes after. So to attention though. Right. So you have your work done, which is per unit volume, so joule per meter cube. What does it help us figure out? Eta হচ্ছে is not the same as strength. So strength মানে কি? How much stress you can apply before it breaks? Strong compare করার জন্য এটা কি compare করে? It compares the toughness of a material. So toughness of a material দেখাতে চাইলে তোমাদেরকে this is the best example. I'm going to show two materials here. Tell me which one can bend the most, deform the most before it breaks. Okay, so this is one, and it can go like that, right? And this is the one that barely goes any much, and then it can snap any moment. Which material do you think can store the most amount of energy before it breaks? The wood, right? And it is considered to be a what material? Tough material. You get my point? Tougher opposite. Eta is tougher opposite. What would you call this material? No, huh? Brittle. Okay. Weak is opposite of what? Strong. Achha, strong are weak opposites. Tough and brittle ki opposites. Okay. So a strong material example ki hobe? Steel, right? Metals. All metals are very strong. A weak material example ki hobe? Plastic, right? Glass. Some glasses are weak. Some glasses are strong as well. What's a very good example of a brittle material? Glass is like the best example, actually. Brittle material. What's a good example of a very tough material? Wood actually very tough now. It'll snap any moment. Steel. I'm only metal is actually everything. So, you know, metal are answered dite paro, but I want something that's unique. Tell me something that's weak and tough. Weak and tough glass now. Graphite. No. Tell me a material that is weak and tough. I know they sound like paradox. How can it be weak and tough? But the thing is, weak and tough কিন্তু toughness is not a synonym for strong. Strong কিন্তু আরেকটা property. Tough কিন্তু আরেকটা property. So it is possible for you to be weak and tough as well. What was that? Play-Doh. Oh, Play-Doh হচ্ছে weak and tough. You're right, actually. Play-Doh works. Play-Doh can be the snap core is very easy, but isn't it capable for me to like stretch and twist it a lot, right? Anyways, I'm going to get the best example of a weak and tough material. Sponge থাকে না for washing your dishes. ওই স্পঞ্জটাকে তুমি now take a piece of sponge and you like twist it, turn it, and like make it into a ball, right? ছেড়ে কি back করে না. So it's very tough. It can bend and deform a lot before anything happens, right? But is it strong? No. And অনেকে বলে যে I think it's strong when it's ছিঁড়া যাওয়া ওরকম একটা problem, and I'll help you figure out how to figure out if something is strong or not. Would you hang from it to save your life? Just always ask this question. If it's strong, yes, you would. If it isn't strong, you wouldn't, right? So একটা ধরো sponge দিয়ে একটা rope আছে and you're asked to hang from it. Would you hang from it? No, right? So it's not actually strong. So strong material would be something that you would like to be, you hang from it. It would take the weight of yours. Okay. So yeah, strong হচ্ছে metals, right? Glass, for example. Let's say there's a glass rod, right? Do you think you can hang from it? Yes, there are certain glass rods you should be able to hang from it, right? So it is actually strong. But glassের কি problem হয়? Bend করতে গেলে bend হবে না, and then next thing you know is what? It breaks, right? That's a what property? Brittle. Okay, so brittle is like একদমই bend করার কোনো scope থাকে না. Clear about that? So yeah, I'll show you more here. But yeah, these are the properties. আজকে গ্রাফটা শেষ করতেই হবে because I won't be doing the graph again. So এখানে copy করে নাও. So sorry. Tough is it can bend a lot before it breaks. Brittle is it doesn't bend at all before it breaks. These are the definitions I'll be provided. Strong is it can take a lot of force before it breaks, and weak is it breaks very easily with a very small amount of force. হ্যাঁ বলো। ইয়েস, ওটা দুইটা গ্রাফের হচ্ছে এরিয়া, দেখবে একটা গ্রাফ একটু আগে শেষ হয়ে যাচ্ছে। হ্যাঁ, ডেফিনেশন গুলো আমি দিয়ে দিচ্ছি, ডেফিনেশন খুবই ইম্পর্টেন্ট। হ্যাঁ, এটার সাথে কপি দিয়েছে, আজ করে দিব। It does. Oh no, young modulus is only applicable for the linear part of a graph. আমরা তারপরে আর বের করি না। So young modulus can only be taken into consideration till the Hooke's limit. তারপর আর ইউজ করতে হবে না। Any graph. And why is it also possible here? Because the stress has force in it, strain has extension in it. So the rule is, yeah, that's the thing. If it's not a regular shape, it will still be stress into strain with a constant in the front, like half or something, right? So eventually the units are what matter. So if it was a triangle, for instance, right, it would be half stress into strain. If it was a rectangle, what would it be? Just stress into strain. So eventually we're looking for units. So stress into strain gives us the same regardless of what shape it is. No. So in the exam, you will. In the exam, they'll give you the shape and they'll ask you to find the area under the graph. And in that case, there's a process called box counting. You count the number of boxes and they ask you for an estimate. Wait, what? 140 কি? 130 হওয়ার কথা তো। 40, 60, 30. A 80%. 104. না, ওটা তো হচ্ছে স্কেল মার্কস। টোটাল মনে নেই, বাট ইউজুয়ালি পেপার ওয়াইজ হয়। সো পেপার 1 হচ্ছে 40 এর মধ্যে, it used to be 25. এই বছর it was different. এই বছরটা যদি নাও, it's all very different, but generally speaking it's 25 থেকে 29 এর মধ্যে to get an A. আর পেপার 2 তে 60 এর মধ্যে 42 থেকে 45 এর মধ্যে এরকম, রাইট? আর প্র্যাকটিক্যালটা হাই থাকে, কারণ প্র্যাকটিক্যালটা if you know you know, if you don't know কিছু পারবে না। সো ওরকম যেহেতু প্র্যাকটিক্যালে দেখা যায় 30 এর মধ্যে 22, 24 এরকম, মানে যেটা অ্যাকচুয়ালি 80% ওটাই আসে। But yeah, এই বছর it was just 80%, so no scaling. Right. ওটা আমি করাতাম, but since you asked বলে রাখি, so what you need to do is you need to find the values of k, the দুইটা k বের করলা, and you find the percentage difference. 1k minus the other k divided by the average in 100%. It's called percentage difference. Right. And if your percentage difference is less than 5%, it's considered to be correct. And when the difference is so small that it's less than 5%. Or 5% cannot, because 5% হচ্ছে acceptable range of uncertainty. How do you find young modulus of a material from a linear force extension graph? You can't. Force extension graph থেকে young modulus বের করা যায় না. Young modulus can only be found from a stress strain graph. Yep. F equals to kx, because এটা তো আর হচ্ছে কোনো ওই যে তোমার ওই হলো ওইটার মতো এটা শেপ হয়ে গেল একটা মেটেরিয়াল আর না। আচ্ছা, সো ইয়াং মডুলাসে কি help করে compare করতে লিখে দিচ্ছি নিচে it helps you compare the stiffness of the material. So if you want to compare stiffness of two material, you look for Young modulus, just like what? Your spring constant. Okay. Energy density হচ্ছে কি compare করতে help করে? Toughness. And what's toughness? এটা আমি একটা definition list দিয়ে দিব এখন. And UTS কি help করতে কি compare করতে help করে? Strength, right?
The UTS is property of material or any of
Material, not shape.
but the example you showed with the two.
Yeah, so if you take these two, right?
Either one is more UTS.
No, you'll have same. I'm বললাম তো, these two have different force that you need to break. But if you find the stress needed to break both of these, same much. And UTS is a stress, not a force.
How many forces is it?
Force is how much actual force applied. Stress is over the area. Are these two the same area? That's why you'll find the stress is same, but what is different? Force. That's why force extension graphs are useless. Okay. আর এই পয়েন্টটাকে বলা হচ্ছে yield region. এটার কোনো রকম significance তোমাদের সিলেবাসে নাই. It just helps you figure out when does the plastic deformation start. Okay. So the red part যেটা আমি show করবো এখন, this represents plastic deformation. This is elastic region. This is your plastic region. Just give me a minute. I mean, definitions গুলো দিয়ে রাখি because আজকে গুলো upload করে দিব. If you have your exam, you can start studying for it. I'm বলিনি কোথায় definitions গুলো. Right, just heads up দিয়ে রাখি এখানে সব definition পাবে. Everything that I have discussed, it's here. So এটা আমি add করে দিচ্ছি.
Sir, past practice question is a velocity time graph chilo. The sir, maximum axis is 10 minus 10. And the question was like this: involving the horizon or the niche action. So sir, it crossed like 3 seconds. Graphing of it, so sir, it will be easier.
Good job.
Yes, sir. This is after graphing the exact graph.
Velocity versus time.
Yes, this is highest to 10. As our lowest to minus 10.
And it's a straight line like this.
Yes, sir. Are it 2 seconds across for it? Are it 3 seconds or minus 6?
Three then.
Yes, sir. It is minus 10.
Yeah.
So, sir, you told me to find the displacement after 3 seconds. From what the people follow, what the bunny jar. This was the graph. There were like find the displacement after 3 seconds. So there were like a lot of options.
Zero.
What?
After 3 seconds, so it went up a certain amount and it went down the same amount, right? So what is the net displacement? Zero.
Sir, A the graph like a triangle, how it is different graph.
This triangle represents going up. This triangle represents going down. Was the answer zero?
Also, like even a portion to like.
আচ্ছা এরকমই হওয়ার কথা আর যদি এটা একটু লম্বা হয় নিচে it means it went up a certain amount but it fell longer.
So does this area mean something?
No, it's always the area under the line. So this area, that area doesn't mean anything.
Oh, okay.
Right, so ওরা বলছে যে horizontal uniform, vertical acceleration হচ্ছে. So this is like a projectile motion, if you could say. It is a projectile motion actually. The graph shows the variation of time and displacement of the object from initial position. Horizontal displacement to the হয়, constant velocity to the হয়, it's supposed to be a straight line. So that can be the answer. Vertical displacement to the হয়, it should increase and increase from rest, object moves from rest, uniform acceleration vertically. So it's a এভাবে বাড়ার কথা. কেন? Because acceleration and graph হচ্ছে more and more displacement per unit time, increasing at an increasing rate.
So for displacement time, if we can
No,
say what the acceleration is.
No, we know what the shape would be, but we can't find the acceleration value from the graph. So shape হচ্ছে A is acceleration. So we can't find the acceleration from here, but we know it's acceleration. So answer হচ্ছে horizontal, এটা হবে D, right?